Greetings, salutations, all those nice things. Welcome to the end of a very short unit for our radical functions. Today we're looking at solving radical equations graphically. And we're going to see two types of radical equations that we can solve graphically. One where we've got everything punched on one side, and the other side is 0. Or another case where you've got expressions on both sides of this equal sign to create the equation. Generally speaking, they're kind of the same. In one sense, what you want to do is graph y equals the left side, graph y equals the right side, and find the x values where they intersect. In the case where one side is 0, though, we can just say that it'll happen wherever we hit the x-axis. As we'll see. Feel free to give this a try if you want. We're going to solve it graphically. We're going to verify it algebraically. So kicking this one off, of course I always make sure I label my axes. And if I'm looking at this particular equation, if I let y equal the root of x plus 6 minus 2, then that's over here, let's see, 6 left, 1, 2, 3, 4, 5, 6, and down 2. So that's the start of this radical function. And then I can transform other points to figure out where this all goes. So this part you should be familiar with. You should know how to transform a radical function. 1, 2, 3, 4, 5. This can go here. Super. And naturally I will play connect the dots. A game not just for children, but for mathematicians too. Maybe detectives. That's more metaphorical at that point. So there it is. On a side note, but it's related, here's what you can basically say. So the point where y equals 0 is the point where root of x plus 6 minus 2 equals 0. That's our key feature here. Where does that happen? Well, it happens where y equals 0. Right there. Boom, done. But we weren't solving for y at any point in time. There was no y in our original statement. We're solving for x. So we better have a statement that tells us what x is. Where does this happen? Where does this point occur? This happens where x is equal to -2. And we can verify this. Now we have a bunch of different types of equations, and some of these types can have extraneous answers. So whenever you verify, make sure you treat the left side and the right side separately. So on the right hand side, we just have 0. On the left-hand side, we have the root of x plus 6 minus 2, which in this case is the root of -2 plus 6 minus 2, and we just continue with this. Minus 2, that's 2 minus 2, that's 0. So the left-hand side is equal to the right-hand side. We good. So we've solved and verified that particular equation. That's done. Now, as stated earlier, we could also have graphed the right-hand side. We could say let y equal 0 and graph that. That's this line right here, known as the x-axis. And it's still that point of intersection with it. That'd be our result. And we see that kind of thing in our next example, where we've got Not 0 on one side, but stuff on both sides. And you might think to yourself, oh, it's no problem. I'll just punt everything over on this side. So we're just dealing with this. Can you graph that? Yes. Yes, you can. Would I want to graph that? No. No, I wouldn't. I wouldn't mind, however, graphing y equals this and graphing y equals that. But as there are two separate functions, I'll need to be able to label them. So I'll let f of x equal this left-hand side. I will let, there it is. I will let g of x equal the right-hand side. And then I can graph each of those. Speaking of scales, should probably be one over here. That can be one. That can be one. All right, I graph these things. With my beautiful color coding. So root of x plus 1, that's just the parent function shifted 1 to the left. That. Pretty important to graph it like you care, as always. So there's our f of x. And g of x, y equals x minus 1. So that's our parent linear function. Boop, 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 boop. Which has a whole bunch of points. Let me just pull out my handy ruler here. And graph that. Whoa, good thing I had the ruler with me. That was close. And this does, of course, go on forever in both directions. While I'm here, I might as well label my scale. According to this, we have a solution right there at that point of intersection. That's where these two expressions give us the same y value based on their current x value. So what's the solution? Solution should be that x is equal to 3, because that's the point of intersection. We could verify this, but we're not asked to verify it. We are asked to solve it algebraically, which will include verification at some point. So let's try that out. If we were to solve it algebraically, we'd say that the root of x plus 1 is equal to x minus 1. And then we do some things. Square both sides. That's our process for getting rid of that square root. You may recall from last year. Right, left side is just x plus 1. Right side is x squared minus 2x plus 1. And that's from, of course, taking x minus 1 squared and saying it's x minus 1 times x minus 1. Don't forget. Blah. And now we solve this thing. Let's get 0 on one side. Let's get everything else on the other. What is this? Minus 3x. So that's it. I will solve this by factoring. And right there I can say that x is equal to 0. Or x is equal to 3. And if we verify, let's verify x is equal to 0. left side is root of x plus 1, which in this case is the root of 0 plus 1, which is equal to root of 1. All right, and the right-hand side is x minus 1, which for this case is 0 minus 1, and that's negative 1. So left side does not equal right side. That's a hard no. Let's check the other one. Could x be 3? Our left side is the root of x plus 1, which is the root of 3 plus 1, which is the root of 4. Why, that's equal to 2. Your right-hand side is straight up x minus 1, which is 3 minus 1 for this particular answer, and that's 2. So the left side does equal the right side. That one is the correct answer. So it's interesting that we can directly see this particular spot here, that we can see that x equals 3 as our legit answer. What about this x equals 0? Why do we even get extraneous answers when we solve radical equations? I mean, it's not a guarantee, but sometimes they pop up. What's the dealio, yo? The issue is with this business of squaring. It's kind of a deal breaker. When we square both sides, we essentially take this radical part and say, well, we could have the positive radical part or the negative radical part. Because if I had an equation that said something like, oh, I don't know, negative root of x plus 1 is equal to x minus 1, how would I solve that? Well, I'd probably still square it, but that would still just give me, well, negative 1 times negative 1 is just 1 times the root of x plus 1. So it gets me to the same, where's that square? Square, nailed it. X squared minus 2x plus 1, nailed it. So it gets me to that same point, even though this one had a negative and that one had a positive. So as a result, we have multiple points brought in that might not have been there before. One of them being based on this graph. And what does that graph look like? Well, it's like if we took this thing and flipped it upside down. This wouldn't necessarily be a reflection over the x-axis whenever you're looking at what causes that issue. In this case it is, just because our starting point for the radical function is on the x-axis. But if you had something like starting up here, well, then your mirror function would be going down the other way. So they all have that part in common. But this is where we can see this extraneous solution coming in. That's where x equals 0 for our other intersection point. That's why it exists, because when we square both sides, we're saying we're not just taking half of this sideways parabola, we're taking the whole sideways parabola. So that's where that comes from. Worth noting. I put a lot of lines into this business. I mean, that's guess what happens when you care about how your graph looks. Anyways, that's the business there. There is some business here, here, that you should deal with at some point in your life. So give it a practice run. Give it a go, give it a try. I did mention that this is the end of just this one topic. We'll have more topics later, don't you worry. So textbook review and then questions from the 2019 January provincial. So this made up, what, 1/15-ish of the exam? Nice little selection here. Ooh, a description one. So give those a try too, but also look at the provincial exam database I have online where you can reference all the questions related to this topic from all the provincials dating back to 2013. Don't forget that exists. It's a very handy resource for practice questions. If you have questions, comments, concerns, as usual, you can let me know either via Teams or in class, in person. The world is your oyster. Crack it open. That's all I got. So long, farewell.